This lesson is section 10.1, lines and segments that intersect circles. As usual, we begin with definition and vocabulary. So we begin with the definition of a circle, which is the set of all points in a plane that are equidistant from a given point called the center of a circle. So the word equidistant is a word that we'll be using a lot from this point forward. Equidistant means equal distance. So if we were to create a point that we call the center point, and we were to measure in all directions and place a point at an equal distance in all directions, and as you do this all the way around and you start filling in all of the points equidistant, as you fill in all of these points, you're going to see the circle forming, and then you get the picture of your circle, which is all points equidistant from a central point. And that central point is what we use to name our circle. So a circle with a center point P is called circle P. And we always try to come up with a notation that is graphic in design. So it's a circle with a dot and the central point next to it. So this is circle P. And this one down here we would call circle C. So some other terminology that comes with circles are radius and a segment whose endpoints are at the center of the circle and at any point on the circle is called the radius. So again, if we were to draw a circle and put a central point, pick any point on the circle and connect it, and you have your radius r. Or I can pick another point on the circle and connect it to the center, and that's another r. And the thing that's true about all of the radii of the same circle is that they're equal. All radii are congruent. The next type of segment is called a chord, and a chord simply has its endpoints on the circle. So we see in this drawing there's a green line segment with the endpoints on the circle, and that's a chord. It does not have to pass through the center. It can't go on the outside of the circle. It's only on the inside. And if the chord does pass through the center, then we get a special type of chord that we call a diameter. So if we look at the picture of the diameter, we see that its endpoints are on the circle, so it is a chord, but it's a special chord that passes through the center of the circle. And we can draw another example. If I have the center of the circle and my chord passes through it, then that chord is known as a diameter. Next, we have a line called a secant. Remember, lines are infinite. They have arrowheads on them. So a secant, as its arrowheads, passes through the circle and intersects at two places. So what we could say is that every secant contains a chord of the circle. Every secant contains a chord of the circle. And we can see right here that just the segment is the chord, but the secant is the line that goes on indefinitely. Next is our tangent line. Tangent lines touch circles at only one point, and exactly one point. And that one point gets a special name. It's called the point of tangency. So in this picture, point B is the point of tangency, and line BA is the tangent line. So now that we've seen some vocabulary, let's apply it to the diagram and see if we can identify these figures using the most precise word. When I say the most precise word, that means if something could be identified as either a chord or a diameter, we would say that a diameter is more precise because there are many chords, but diameters are special types of chords, so that would be the more precise word. So let's look at this. For part A, we're looking at AC, and if you trace from A to C, you say, well, I have an endpoint at the center and an endpoint on the circle. So for part A, we would say that AC, which is a segment, is a radius of circle C. And then part B, we're asked to look at segment AB. So let me erase what I have here. Now we're looking at segment from A to B. Its endpoints are on the circle, so it is a chord, but because it also passes through the center, it is a special kind of chord, so the better name to choose would be diameter. AB is a diameter of circle C. Now if we look at question C, we see that they're using the notation for a ray. So ray DE. Let me erase my markups here. And we're going to start at D, that's our endpoint, go in the direction of E, and it's going to go on indefinitely that way. And we see that this ray touches the circle at one point, and that one point is B. So we can say that ray DE is a tangent of circle C. And just to add some emphasis here, we can say that point B is the point of tangency. And then finally, our last object is line AE. Notice it has the double arrowheads over the letters A and E. So when we look at line AE, we see that this line passes through the circle in two places, but it has arrowheads on both sides. We would call AE a secant of circle C. And that secant contains a chord. The chord it contains is AG. Okay, so this was just taking the vocabulary that we saw on the previous slides and looking at an image, making sure we can identify these parts correctly. Again, that is an important step for the theorems we're going to learn, for the problem solving we're going to do. Back to vocabulary and definitions. In a plane, two circles can intersect in 2 points, 1 point, or no points. Coplanar circles that intersect in 1 point are called tangent circles. Coplanar circles that have a common central point are called concentric circles. So concentric circles have the same center point, but they have no intersection points. And we can see right here, we have a picture of concentric circles. They have a common central point and they don't intersect. You can also draw circles that are far away from each other that don't intersect. Here we have circles with exactly one intersection point. Notice that on the left we have a circle inside of a circle, but they touch at one point. And on the right we have a circle outside of a circle that touch at one point. Those are tangent circles. And then you can make overlapping circles that connect or intersect at 2 points. To extend on this, they define what's called common tangents. A line or segment that is tangent to 2 coplanar circles is called a common tangent. A common internal tangent intersects the segment that joins the centers of the 2 circles. A common external tangent does not intersect the segment that connects the 2 circles. All right, so we're going to draw 2 circles. I'll call this circle C, and I'll call my other circle circle P. And if I draw a tangent between these 2 circles, that means it's a line that touches each circle at exactly 1 point. That makes it a tangent of the 2 circles. It is a common tangent, but now we're going to show that it is an internal common tangent, because if I draw the segment that connects the center of these 2 circles, we see that these lines intersect, so that makes this an internal common tangent. However, I can draw a different common tangent. And if I draw a tangent that touches these 2 circles here, and we say, well, now let's draw the segment that connects the centers, notice that this tangent does not pass through that segment that connects the center of the 2 circles. So we would call this an external common tangent. So an internal goes between the 2 circles, an external does not go between the 2 circles. That's another way to look at it. but we just wanted to examine the book's definition. So now, drawing and identifying common tangents. So look at question A. How many common tangents can you draw? How many of them are internal? How many of them are external? So it says, tell how many common tangents. Use blue for the common external. Use red for the common internal. So I can draw a common external here and here, 1 point each that they touch. And I can draw a common internal this way and this way, 1 point each that they touch. And we would say there are 4 common tangents. 2 of them are external, 2 of them are internal. And now you can look at the next one, try it yourself, pause the video, see how many common tangents you can draw, and then unpause to see the answer. So here we see the 2 circles touch. I can draw a line that goes right through here for 1 internal common tangent, but I can draw lines here that are 2 external common tangents. So here we have 3 common tangents. 2 external, 1 internal. So for example C, there are no internal common tangents. We can't draw an internal, but we still have our external common tangents. So we would say 2 common tangents. 0 internal, 2 external. So here we begin our theorems. Our theorems often give us rules we can follow so that we can solve mathematical problems with these rules. Theorem 10.1, the tangent line to circle theorem states that in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of that circle at its endpoint. A radius or diameter with one endpoint at the point of tangency forms a right angle. With the tangent line. And this is going to be huge for us because look what I'm drawing here. I can draw, and I formed a right triangle, Pythagorean theorem, trigonometry, all of these fun things are going to come into play. So whenever we see right angles inside of our circles, we will be able to create right triangles and use everything from the previous chapters. Theorem 10.2, the external tangent congruence theorem, states that tangent segments from a common external point, so we see in here that S is a common external point, RS and ST share point S, right? That's what makes it common. So tangent segments from a common external point are congruent. So that means that we can put the congruent tick marks on here, saying those two are congruent, and that's going to let us use properties of isosceles triangles and whatnot. And because these are tangents, that means that I can even make right triangles in here. So there's a lot of different properties that we're going to be able to use here. So here's an example where we can try to apply these theorems. It says, is ST tangent to circle P? Well, here's ST. And if ST is tangent to circle P, well, PT would be a radius. That means if they form a right angle, then it's tangent. If ST is perpendicular to TP, then ST is a tangent of circle P. And then I ask, how can you show that that's a right angle? What can you use to prove that that's a right angle or not? And hopefully you say, use the Pythagorean theorem. So remember that our hypotenuse is always across from the right angle. So that's our C value. And then we can make the other two A and B. A and B are interchangeable, but C, we have to get that one right. So that means that A squared plus B squared equals C squared will become 12 squared plus 35 squared equals 37 squared. And 12 squared is 144. And you plug 35 squared into your calculator, you'll get 1,225. And then you plug 37 into your calculator, you get 1,369. And you say, do these two add up to be the same? And you get 1,369 is equal to 1,369. And you say, yes, this is a right triangle. And if it's a right triangle, that means that angle T is a right angle. And if angle T is a right angle, that means that ST is a tangent of circle P. And we've answered our question. Here's our next one. It says in the diagram, point B is a point of tangency. Once they tell us that's a point of tangency, you can draw a right angle in there. Find the radius R for circle C. Well, if that's a right angle, that means we have a right triangle there. I'm going to draw the right triangle out of the diagram. And I see that the bottom side is 80 from A to B. And then from B to C, we see that that is R long. And then from A to C is 50 plus R long. We see that we traveled a blue segment, which is 50, then another R, and that's 50 plus R long. So once we take all of that, we say, great, I've got all of my sides. I'm ready to do my math. It is a right triangle. Pythagorean theorem is what we're going to use. A squared plus B squared equals C squared. We have to get the C squared right. That is the hypotenuse across from the right angle. So C is equal to 50 plus R. That means that we can make the other two A and B, doesn't matter which order. So we have R squared plus 80 squared equals parentheses 50 plus R squared. R squared plus 6,400 equals, and remember we have to write this twice, 50 plus R times 50 plus R, and when we use distributive property we get 2,500. That's the 50 times 50, and then 50 times R is 50R, and then we have an R times 50, that's another 50R, that makes 100R altogether, and then R times R gives us R squared, 2,500 plus 100R plus R squared. And now we want to combine our R squareds. We always start with the highest exponent first, because if it cancels, which it does, we don't have to factor. If the R squared did not cancel, we would need to factor to solve this. Now we'll subtract the 2,500 to the other side. That gives us 3,900 equals 100R. And then you divide both sides by 100. And that gives you 39 is equal to R. So in the diagram, point B is the point of tangency. Find the radius R of circle C. R equals 39 feet. And our last example, it says RS is a tangent to circle C at point S, and that RT is tangent at circle C at point T. Find the value of X. And this is the common external point for the common tangents. And our theorem told us that these common tangents would be congruent. So RS is congruent to RT by external tangent theorem. So we can set 28 equal to 3x plus 4. Subtract 4 from both sides, and you have 24 equals 3x. And when you divide each side by 3, you get x is equal to 8. So that's the end of this presentation. You can go back and watch the video again, take notes, come to class with questions. All right? Thank you.